Welcome to this edition of Models 2 ACE. Further to and in continuation of our previous video titled Forecasting Models on Time Series Forecasting of Sales, which use non-causal methods that use historical data of sales to forecast the future values of sales, this video builds on trends and seasonalities towards advanced forecasting. Let us take up the same dataset for this problem. We have the quarterly sales data available for a product for 4 consecutive years, and for each year, the granularity of data is at the quarterly level. So, we have sales data available for 4 years or 16 quarters from the first quarter of the first year through the fourth quarter of the fourth year. We will use this data in various models to predict the sales data for the corresponding 4 quarters of the fifth year. Let us plot the data in a time series graph. Let's add a trend line to examine the presence of trend and, if present, the direction of the trend, that is, whether it is trending upwards or downwards. We note that demand is trending upwards year on year. Seasonality 2 is present. Let us take up the same dataset for this problem. We have the quarterly sales data available for a product for 4 consecutive years, and for each year, the granularity of data is at the quarterly level. So, we have sales data available for 4 years or 16 quarters from the first quarter of the first year through the fourth quarter of the fourth year. We will use this data in various models to predict the sales data for the corresponding 4 quarters of the fifth year. Let us plot the data in a time series graph. Let's add a trend line to examine the presence of trend and, if present, the direction of the trend, that is, whether it is trending upwards or downwards. We note that demand is trending upwards year on year. Seasonality 2 is present in the data, and we can note that the seasonality or periodicity of the cycle is annual. The peak and off-peak periods, marked by the circles, repeat every year. Let us quickly revisit the moving average model, which we had detailed in the previous video titled Forecasting Models. Note that the moving average itself is increasing year on year, further confirming that demand is trending upwards. Revisiting the model Simple Exponential Smoothing, we observe that the model is able to capture trend. Here, the value of A or alpha is 0.4. The forecast for the first time period is same as the demand for the first time period. The second month onwards, the forecasted value is calculated using the model. The model has smoothened demand to an extent as sharp peaks and troughs are removed in the forecasted values. Since this model does not account for trend and seasonality, the forecasts for the next 4 time periods in the fifth year are the same. The model Double Exponential Smoothing, also known as the Holt model, incorporates trend. The term double in the name of the model refers to the presence of the 2 exponential coefficients, A or alpha, and B or beta, corresponding to level and trend. Here, the values of A or alpha, and B or beta, are both equal to 0.4. The forecast for the first time period is same as the demand for the first time period. For the second period onwards, the forecasted values are calculated using both alpha and beta. Note that these randomly selected values of alpha and beta may not be the most optimal values. For choosing the optimal values, one should choose either one of the 2 forecast error metrics, viz. RMSE, root mean square error, or MAPE, mean absolute percentage error, and determine the best fit statistical forecasting method that minimizes the error metric. This blue-colored graph is the trend line that has been added on top of the level forecasts to obtain the final double exponentially smoothed forecasted values. The next model, the first of 2 versions, named Holt-Winters models, incorporates both trend and seasonality. This model is also known as the Triple Exponential Smoothing model, as it uses 3 smoothing coefficients, alpha, beta, and gamma, for level, trend and seasonality. First, we calculate a statistic, known as the Central Moving Average or CMA, over a cycle comprising of 4 quarters. The CMA for a time period, say the third time period, is calculated using a block of 4 successive time periods, such that the third time period is at the center of the block of 4 and has equal time periods before and after the central point. However, in the present case, since the cycle or block size, 4 itself is an even number which cannot be bifurcated in such a manner, we perform a workaround. We calculate the average of the block of the first 4 time periods, 1, 2, 3 and 4, cells D7 to D10, and another average of the next consecutive block of the next 4 time periods, 2, 3, 4 and 5, that is cells D8 to D11. We finally take the grand average of these two calculated averages to arrive at the final CMA for time period 3. Obviously, such a CMA cannot be calculated for time periods 1 and 2, as we do not have enough data for these two time periods. In this next column, we take the ratio of the actual sales divided by the calculated CMA. This is because the CMA is a proxy for the level and trend, since the 4-period average essentially deseasonalizes or removes the seasonality from the data, seasonality having a cycle of 4. So, sales divided by CMA is sales without the seasonality. Hence, in the next step, when we proceed to take the ratio of actual sales divided by the calculated deseasonalized sales, we get the seasonality index. To take a concrete example, we observe here that in quarter 3 in year 1, on top of level and trend, the sales went up by 13%, attributable to seasonality. In quarter 1 of year 2, sales went down by 4%, beyond the value attributable to level and trend. Now, since we know that seasonality is yearly, and in every third quarter it bumps up sales by 10% to 13%, we want to calculate a generalized third quarter average seasonality that will hold true across the years and can be used in calculating the forecasted value. To calculate the seasonality for a quarter, say quarter 3, we take the average of all such calculated seasonality indices, that is 1.13, 1.10, and 1.14, corresponding to quarter 3s across years 1, 2, and 3. Similarly, we calculate average seasonality indices for quarters 2, 3, and 4. Then we convert the seasonality indices into a normalized seasonality index, NSI. This is because this sum of the 4 quarterly seasonality indices should ideally have come to 4, but it does not due to some errors that creep in. So, we perform this normalization operation to make these seasonality indices analytically consistent. So, we observe that quarter 4 is the highest peak period, followed by quarter 3, the next peak period, whereas quarters 1 and 2 are off-peak periods. We then carry over these NSIs to this column G, in the model. We then use these NSI values to deseasonalize the actual demand or sales. So, dividing the actual sales D7, by the NSI G7, gives us the raw data of deseasonalized sales, in column H, on which we will forecast level and trend. Finally, we will add back the seasonality index to get the final forecasted value. To achieve this, in the column SLR, we perform a simple linear time series regression or straight line forecasting on the deseasonalized values in column DS sales, which contain only level and trend and have been stripped off seasonality. We use Excel's inbuilt forecast function for simple linear regression, using time as the independent variable. Please note that this is not a causal regression, but a time series one. So, column I, SLR trend gives the forecast that factors in both level and trend. Note that in this model, we are not bothered about alpha and beta. Instead, we will simply adjust the coefficients, A and B, in the linear regression to optimal values that will minimize forecast error, RMSE. The derived values A and B will be used again to regenerate the new forecasts. All these steps are performed behind the scenes by Excel's inbuilt forecast function for simple linear regression. Column K contains the general forecasted values, after incorporating seasonality using the normalized seasonality index, calculated previously. The column L, MAD, contains the mean absolute deviations or errors, that is the absolute values corresponding to the values I column J. The last column, M, contains the percentage values of the mean absolute deviations or errors, calculated with respect to the raw, deseasonalized sales values. In this next model, another variation of the Holt-Winters model, instead of using Excel's forecast function, we have used the formula of triple exponential smoothing. We have simplified the formula by collapsing A, B and C into a single parameter, alpha, and carry out exponential smoothing. We have frozen the coefficient value of alpha that minimize RMSE. Here, though MAPE is slightly higher than the SLE model, it is still good. This column less trend has the exponentially smoothed values, using the parameter alpha. In this figure, the green-colored graph represents sales, the blue-colored graph depicts CMA, the maroon-colored one is the forecast that captures only level and trend. Thank you for your valuable time in this video. Please subscribe to our channel for more advanced analytical models.